Okay, so how does water go from the surface to the ground? It goes from the surface to the ground through a process called infiltration. And infiltration involves water moving through the individual openings, which are called pores, in the soil or the rock or whatever. So these are supposed to be sand grains or grains of dirt, let's say. This is air up here, and you got some roots and some plants going down there. There's a flower. Okay. So when a drop of rain falls from the sky, that's a drop of rain, it hits the surface, it piles up, and then it's going to begin to move down through the pores like that, right? It's got to go just through the openings. It can't go through the grains themselves. When we look at, if you just keep piling water up drop after drop after drop and measuring the rate at which it soaks into the ground, there's something kind of interesting happening, which is that the infiltration rate, which is high here, over time, it starts out very, very high, and then it kind of decreases and eventually levels off. And this leveled off value is called the steady state infiltration rate. Steady state infiltration rate. And steady state simply means that it's going to stay that way forever, right? It's the steady state. It's the long-term value. So from time zero, which is here, infiltration rate begins very high and it decreases exponentially. You're used to these exponential decay curves now from looking at flood recession and other things. And eventually it plateaus and it'll just stay like that forever. So the question is, why? Why does infiltration rate start high and begin to slow? And the answer is that each one of these, I'm going to sort of zoom in here on the surface of the earth and sort of draw it kind of like that. Each one of these little empty spaces in here, they're all connected, you can kind of draw it like that. You can think of it like a straw, or better yet, a capillary. And you may have noticed in your Coke or something, if you put a straw into your Coke, that the water level or the level of Coke inside your straw, it might actually stick up slightly higher than the surrounding water. I don't know if you can see that. I'll kind of draw it for effect there. So it's a little bit higher than the ambient level. And that's because the surface tension, the sort of attraction between the inside of the straw and the liquid draws that liquid up inside the straw. And capillarity is big, when the straw is very big, capillarity will be very small. But as the size of the straw gets smaller, capillarity gets bigger as well. So that when you have very, very, very small openings, the height to which the water or the fluid or the Coke or whatever is drawn up inside the tube is higher and higher and higher. So what does that mean? Well, that means that in the pores, these open spaces between the grains in a soil or in a rock, are acting like capillaries, but instead of drawing the water up, they're drawing the water down. So when a drop of water lands on the surface here, there's a drop of water, it gets sucked into the pores by this capillary force. Now, as the water gets sucked in, you're going to be filling these pores. You're going to be saturating the pores with water. And as you do, the capillary force is going to become weaker and weaker and weaker over time. And that's why the infiltration rate is going to drop, drop, drop. So by the time you get to this steady state infiltration rate, what physically has happened to all of the pores over here in this soil? I'm asking that as a question to you to think about it for a second. What does it mean when you've reached, in terms of the pores of the soil, when you've reached a steady state infiltration rate? What does it mean? It means, that's right, very good. It means that all of the pores are saturated. There's no more open space left in these pores to suck the water in, and therefore capillarity essentially has gone to zero, and the rate at which the water moves through is due to the sort of permeability, as we'll call it for now, of the soil itself. All right, so that's that. Now, when you look at how water infiltrates, or what happens to it when it infiltrates into the soil, what we see is, if this is depth in the soil, here's the soil top again, so there's a flower. If you start out with a dry soil and you put a layer of water on top of it, so this is a dry soil, and this is just a slug of water that we've just plopped down on top of the ground. What happens is that the water infiltrates downward, right? It's going to soak in, and what you're going to get is essentially what's called a wetting front. So this will be saturated as this water here moves in. This will become saturated, meaning all of the pores, all of the empty spaces are filled with water. And that slug of water is going to migrate down. So if we look at the slug of water, it's going to be here, and then it's not going to be here, right? So think of this as like water content. This would be 100% of the pores are full of water, and 0% are filled with water. And here's the depth in the soil. So you get this very dry soil. This is all dry down here, and everything up here is saturated with water. If you come back and look at it a little bit later, what you'd see maybe is something that looks kind of like this. So this slug, essentially, of water is migrating down, and we're actually losing some of the water up in here. So this is now not saturated, some percent saturated. Forgive that. This is saturated, but everything in this curve, essentially, is saturated with water. And then if we come back a little bit later, we might see something that looks kind of like this. So what you can see essentially is that this slug of water that we put on top is migrating down from here to here to here, and below it the water hasn't gotten there yet, right? So maybe you can't see that. Below it the water hasn't gotten there yet, so this is still dry. Above it the water has to some degree drained out. So this was saturated at one point, but now some of the water has drained out. And we've got about 30 or 40% of the pores in here are now saturated with water, right? So again, what we're looking at is not a vertical slice necessarily through the soil, but with depth, we're looking at what percent of the soil, 0 to 100%, is actually saturated with water. And so it looks something like this over time, these slugs. Now, when you think about the rate, of, did I write down wetting front? I don't know if I wrote that down. This is called the wetting front. You think about the rate of wetting front advance. How fast is that water going to migrate down? Well, let's assume that the soil here, has a porosity of 50%. Now, what all that means is that 50% of the soil is holes. 50% of it is rocks and roots and whatever, and the other 50% is empty space. So if you were to put, let's say, 10 millimeters of water in a slug on top of the soil, and you watched it, and that water was dropping at the rate of 1 millimeter per minute, right? how fast would this wetting front be moving down? Remembering that it can only move through the pore space. How fast would the water be moving? If this pure slug, this is nothing but water up here, it's dropping at a rate of 1 millimeter a minute, and it's going into a soil that has only 50% porosity, 50% pore space. If this is dropping at 1 millimeter a minute, this wetting front has to be advancing at how many millimeters per minute? It has to be going twice as fast because it has half as much space to move through. So the rate of wetting front advance would be 1 over the porosity, 1 over porosity, which would equal 2.0 millimeters per minute. That would be the rate at which this thing is moving down. Okay. Last thing to think about is infiltration versus runoff. Remember runoff? Runoff is what happens when water moves across the land surface, eventually makes its way to streams. When does runoff begin? When does runoff begin? It starts to rain. It's raining on a land surface. When does the water actually start running off and moving downhill? The answer, in the most fundamental sense, is runoff begins when precipitation rate is greater than infiltration rate. Right? So if the rain is falling at a rate lower than the infiltration rate, if the water is being added to the soil more slowly than the soil can soak it up, the water will just keep getting soaked up by the soil, and you won't get any runoff. It's only when the precipitation is falling faster than the soil can soak it up that you begin to get water ponding on the surface and then running off. So we can sort of look at a graph, then we might draw like this. Let's say that we have, here we'll just kind of do a dashed line. That is precipitation rate. And we'll just have a fixed amount. This is rate over here, and this is time. That's precipitation rate, and that's infiltration rate. Okay? So what we're saying here basically is that at time 0, it starts to rain. That's precipitation, and it starts to rain at a constant rate, and it just stays that way, right? So what happens if the precipitation rate looks something like this? Remember, infiltration rate is going to start high, and it's going to decrease exponentially until it plateaus at some steady state rate. And it's going to decrease because we're filling the pores in the rocks or soil with water as opposed to air, and so we're reducing capillarity. So what happens in this situation? If the precipitation rate is constant here, the infiltration rate starts here and plateaus here, what happens? Well, in all cases, at all times, the infiltration, let's do it this way, precipitation rate is less than the infiltration rate, and therefore no runoff. It's all getting sucked in, right? Let's look at a different scenario here. What about something that looks like this? Again, rate increasing here, time increasing here. Dashed line is precipitation. I'll move the precipitation up. And now we get something that looks like that. What do we get? Well, from time 0 to time 1, whatever that is, what do we have? From time 0 to time 1, time 0 to time 1, we have infiltration. Why? Because the infiltration rate is greater than the precipitation rate. For the next period, let's call it to time 2. I'll just draw a line here. There's this amount of rain, which I'll color in here, which is the difference between the amount that's falling and the amount that can be soaked in. And you might think, well, okay, that's runoff. But in reality, there's an intermediate step, right? The water doesn't just run off, it fills in the low spots. And we call that depression storage, which I always thought would be a good name for a punk band. Depression storage, so that's puddles and filling in the cracks and the low spots. And then once you've filled up all the low spots, then after that you get runoff in this amount, right? Runoff, sometimes again called overland flow. And that's how it works, okay? So there are a lot of characteristics that are going to determine the infiltration rate of a material and how that infiltration rate changes over time. And we'll come back and talk a lot more about those soon.